Hi, I'm Seth, and in this video I'm going to show you how to create your own z-table, aka unit normal table, as well as your own t-table, f-table, chi-square table, and in fact any sort of table that you would like to create. I'm going to do this unedited, just one take from top to bottom. This will make it a little longer than my videos typically are, but I figure if you're the kind of person who wants to create your own z-table, you probably don't mind taking the long way around. Now, with that being said, I am in nature, so you may hear all sorts of animal sounds or occasionally a boat going by. If so, I'll just try and pause. But yeah, this will be the reason I'm doing it this way is because I want you, who, if you're newer to R, I want you to see, if you're newer to programming, I want you to see how it's done. It's just not, it's not this it's not as effortless as I might make it look in some of the videos I create, where I just write this code and it immediately does whatever I want. We call it code development. That's something I heard Richard Landers say once. It's code development because you're putting it together incrementally. You're developing. It's not something you just write from top to bottom. Okay, so with that in mind, let's go ahead. First, what are we doing? We're gonna make also, if I pronounce things weird, it's staying in. We're gonna make these tables. We're gonna make a z table, a t table, an f table, and a chi-square table. The first one is more of a pain than the others, but it's really not that bad. Um, why would you do this? Well, if you're like me, you may have. So these tables are available. You can find them online. You can find them in the back of statistics textbooks. But if you're like me, you sometimes look at them and you're like, yeah, but what if I want a different alpha level? Or what if I need more than 100 degrees of freedom? What if I need 113 degrees of freedom? Well, I'm going to show you how you can create your own table to whatever specifications you like. But I have already created these. These are what we're going to use as references. So if it seems like I'm just cranking this code out like it's nothing, it's because I've done it before. Okay. So yeah, let's start with the z table, aka a unit normal table. Okay, and the first thing we need to talk about is what this is. So these values, all these tabled values, give us the proportion of a normal distribution that lies to the left of a particular z-score. Okay, so proportions range from 0 to 1. If that sounds unfamiliar, it might sound more familiar if you multiply it by 100, in which case it becomes a percentage ranging from 0 to 100. So let's look at this table and see what this means. The normal distribution is symmetrical, so we have z-scores that are below the mean. That's all these negative z-scores. We also have z-scores that are above the mean. These are the positive ones. This table ranges from about -4 to +4, which contains almost all of the scores in a normal distribution. How do we read this? Look at the left-hand column. That gives us a z-score to the 10th place. And then up top, each column represents a different hundredths place. So for example, if we were looking at -3.0, just straight up negative, a z-score of -3.7, that's right here, because we go to -3.7 to the 10th place, and there is no further decimal, so it's just a 0, 0. And so this is the proportion that lies to the left of that z-score, 0.0001, or if you want to express it as a percentile, bump the decimal 2 spots to the left, and it's 0.01%. Or if we wanted to look at, like, I don't know, -3.74, then go to this row, -3.7, and then find the column with the 0.04 in the hundredths place. That's the proportion to the left of -3.74. Okay, a few things to know about this table. It's going the most extreme, smallest, the most negative z-score is right here. It's -3.99. This is the smallest proportion in this table. It seems the same as this, but that's just due to rounding. It's actually smaller than that one. And so the values are going to get larger as we go from right to left, because negative 3.99 is more extreme. It's more negative. It's lower than negative 3.91 over here. So this proportion is larger. So it's going to get larger as we go from right to left, and then, down to the next line, larger as we go from right to left, down to the next line, etc. This will go on until we reach 0, which is at the 50th percentile, and then the scores start getting larger as we go from left to right. That may be a little confusing at first, but that's just reflective of the fact that we wanted to keep the 0.00, 0.01 in the same order, regardless of whether it's a negative or positive z-score. So you just kind of have to remember they'll get they'll get larger from left to right up until they hit the 50th percentile, and then it flips and they start getting larger as they go from left to right. Okay, something else that's weird, we actually have one duplicate value. There are 799 values between negative 3.99 and positive 3.99. But we have 800 values in this table because we're throwing in a little duplicate. We have the 50th percentile twice. That's because I could have left this one blank. There's really no such thing as negative 0.00. That's just not really anything. But to make it look more complete, I went ahead and just duplicated that. But that's the 50th percentile. It just means 0. And here, negative 0.01. So it is a useful row, but that's not a useful value right there. Okay, so those are a couple of weird things we're going to have to account for, and that's what makes this one take a little bit longer than the others. But yeah, let's get into it. Let's just do it real quick. So we're going to do this in R, and I work in RStudio. So the first thing that we need to do is, let's just get let's get a package we'll need. I'm going to load the tidyverse. Now, this will have a bunch of functions that are useful for data manipulation. If you have never installed the tidyverse before, make sure to install it first using code like this, install.packages, and then put tidyverse in quotation marks. This isn't the only way to do it, but that's how I typically do it. And once you've installed, you won't have to do that again. You can just load the library like this. So the library is loaded. Next, there will be a few more packages that we need to load, but I'm going to hold off on those until we get to them. So let's see. First, I'm going to create some z-scores. I'm about to create something called a vector. A vector is just like a column or a row of data, all of the same type. So you can probably just think of it like a column on its own. So let's see, this will be Z's. Z plural is, let's see, I'm going to create a sequence from negative 3.99 to positive 3.99, going by hundredths places. So that's what this code says. This code is instructions for the computer, but if we put it into human speak, we would say, create a sequence of numbers from negative 3.99 to positive 3.99, going by 0.01 with each step. So like the first one would be, wow, that bird is like right up on me. The first one would be negative 3.99. The next would be negative 3.98. The next would be negative 3.97, etc., all the way until we get to positive 3.98, positive 3.99. And I'm not including the 4 and the negative 4 just because, as you can see in this table, it would just add another row. So I'm just going to end it at 3.99. Okay. And then whenever I say equals, that means I'm assigning it. So now after I run this code, that's what ZS means. If I say, hey, what's ZS? Well, it means all of that I just said. It means start at negative 3.99 and then increment by 0.01 over and over till you get to 3.99. And that's 799 values. We can check that. You can actually see that in the console, but we could check it using a function called length. Yep, we've got all 799 there. but we're missing one because we're going to need a duplicate. We're going to add another 0. As a reminder, we're going to need a -0 right here for things like -0.01, -0.02, etc. So first, let's find where that other 0 lives. We can use this code which z's equals 0. What this code says in human speak is which position is 0 at in the vector that we call zs. Ours says it's at the 400th position. All right, so I'm going to add a -0 right before that. Or actually, I'm just going to add another 0 because -0 is going to confuse R, so I'm going to have to do that toward a later step. So here's how I'm going to add this. I'm going to say now z's is equal to a combination of things. It's going to be first itself at the first through 399th values. Then it's going to be a 0. Then it's going to be itself at the 400 through 799th values. And then this is something I'm going to do a lot. After I write some code, I'm going to give a semicolon, and then I'm going to tell it to print or just return the thing I just did so that I can see what it looks like. Okay, so here we go. Do we have, yeah, here we go. The extra 0 is now here. And if we look at the length of z's, it's now 800. So that's what we want. Okay, so off to a good start. Let's see. Now there's different ways. Okay, so first of all, how do we find the proportion to the left of a given z-score? You can use this code, p norm. That means what is the proportion to the left of a given z-score in a normal distribution. So, for example, if we say p norm for 0, that's going to be 0.5 because half the distribution is to the left of a z-score of 0. P norm of -1 is about 16. Okay, so we need to do that for each of those values in z's. There's a few different ways we could do this, but I'm going to do it in a way that occurs to me. It's not the only way, but it's a way, and it works. Let's see, I'm going to say probabilities. The probabilities are, how do I want to do this? Oh, let's make a bunch of zeros. What this code does is it's going to make a vector, a numeric vector, just full of zeros, just full of nothing, but it's the same length as z's. So there you go, a bunch of zeros. In fact, there are 800 zeros right here. Now let's fill them in. I'll do this with a for loop, not the only way, but it's one way. So for each item in z's, we're going to, how do we want to do this? I'll go ahead and break this into multiple lines. This is how you'll commonly see for loops expressed. It doesn't have to be this way, but this is popular, so I'll do this. I'll say for a given value, a given item in this vector I made called probs is equal to p norm for z's at I. Okay, so this code, if I've written it correctly, what it's going to do is it's going to say for each position in this list of 800, so like the first one, it will run the p norm code on whatever's in the first position of the z's vector. Okay, so that's what I want, because I want a p norm for -3.99. Then it's going to go through, and for the second position, for -3.98, it's going to give me the probability or the proportion to the left of that. So I'm just going to leave it as I for item. And that's what this code's doing. It's saying for each item in this vector called z's, we're going to find the proportion to the left and throw all of those into this probs vector. So let's see what it looks like. Okay, so this is in scientific notation, and I don't want that. So I'm going to say, did that work? Yeah. Okay, so I use this code. I'll put it above. Options, open parentheses, scipan equals 999. I'm disabling the scientific notation. So here are these proportions. It's way more precise than what I was going for, though. So I'm gonna reduce those. I'm gonna say probs. Well, okay. So first of all, this will be instructive if you're new to R. If I just say round probs to the fifth decimal place, that's what this function does. It will round everything to the fifth decimal place. It will do it. And you can see that here we have all 800 and they've been rounded to the fifth decimal place. But if we try to refer to probs again in the future, it's back to normal because we never actually changed it in the first place. This is sometimes confusing when you're first starting out with coding. But this code, it's doing an operation. It's rounding everything to the fifth decimal and showing you that, but it's not actually changing this variable, this vector. If we want it to change, we have to assign it to that. So I'll say probs is equal to itself rounded to the fifth decimal place. And now, now whenever I say, hey, what is probs? It says, well, it is that vector rounded to the fifth decimal place. That's what we've got here. Okay, so this is good. And do we have two 50th percentiles? Yep, those are the two zeros. The proportion to the left are 0.5. Okay, so we've got our probabilities. I'm going to put these into a matrix, I think. Maybe I should put them into a data frame or a tibble, but I'm going to put them into a matrix just because I know. So here's how I code. I go with whatever solution pops into my head in the moment, and it's not always the best. It's not always the fastest or most efficient, but it's what works in the moment, and that's kind of how I code. And sometimes that means I come back in the future and update it to make it more efficient, and maybe I will. But right now, I'm just going to start with a matrix because that's a way I can do this that will work. Now, whenever I'm doing this, so I should say a matrix is a two-dimensional object, so like a rectangular object, and you'll see one in a minute. So like actually, this is a matrix. This Z table is a matrix. It's all the same kind of values split up into columns and rows. So to create a matrix, and I'm going to call it ZMAT, that's my matrix of Z-scores, it is going to be equal to use the matrix function, which creates a matrix. And I'll say, make it out of this, all of the values in probs. Then I'll say in call for number of columns. I would like 10 columns because if we look here, you'll see there are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 different columns. And then I'm going to say by row equals true. I'm going to let this car drive past real quick. Sorry about that. Okay, so by row equals true means I want it to enter the values row by row. So first fill the first row with data, and then fill the second row with data. Otherwise, it would fill them by columns. It would fill the first column, then the second column, and that's not the way that we have the data. Okay, so let's see if this does what we want. I'm going to use a function called view, capital V-I-E-W. Okay, so yeah, this appears to be working. We have 10 columns and 80 rows. However, as you can see, the values are increasing from left to right, which makes sense because that's how we input them. So we need to flip the rows around so that they go from smaller to larger, from left to right. Sorry, I'm being attacked by bugs. Okay, so one way we can do that, God, I hope y'all can hear over this bird. It's like, they're like partying in the tree next to me. Okay, so one way that we can flip these rows is using the reverse function. This just reverses something. So like if we reverse the numbers 1 through 3, it would become 3, 2, 1. So it's just flipping things around. So we need to be careful though, because we don't want to do that to everything. Hold on, let me make sure I haven't forgotten anything. Yeah, I think we're good. Okay, yeah. So I could reverse them one row at a time, but that would be kind of a pain. So I'm going to use the apply function to reverse them all at once. So now remember, I don't want to reverse all of them. It's actually just this first 40 rows. I want everything up through here to be reversed. But then the rest of it, I like for it to be increasing as it goes left to right. So I'm going to keep that the same. So I'm just going to say the Z matrix only at the first 40 rows. All right, 1 through 40. Then I'm going to say 1 for reasons I'll explain in a minute, and reverse. So if we read this in human speak, this means we're going to apply the reverse function to the first 40 rows. And the 1 specifies that we're dealing with rows. That here, I'll just show you real quick. If you need to know more about a function, you can use the help function and then just throw the function you want to learn about in as the argument. This will pull up the documentation. And as you can see, the first argument is just whatever data. In our case, it's a matrix. Then the margin, it's whatever the function will be applied to. Okay, so for example, for a matrix, 1 indicates rows. That's what I want. I'm trying to do this to rows. So that's why I'm using a 1 as that second argument. Then the third argument is just whatever function you want to apply. So I want to reverse them. So the documentation, the help files will be extremely useful to you. Okay, so let's see. Let's see what this does real quick. I'm gonna view it. Okay, we now have 10 rows and 40 columns, which means it's been transposed. Transposition means that you've made your rows into columns and your columns into rows. So you've basically kicked the matrix on its side. So I'm not actually 100% clear on why. Maybe applying the reverse function also reverses what's a column and what's a row. I actually don't know, but it kind of doesn't matter because I can just flip it back the way I want using the transpose function, which is T, the T function, T for transpose. That's just going to take it and make it so the columns are rows and the rows are columns. So for whatever reason it was just flipped, this is going to unflip it, okay? And yeah, let's go ahead and view what that looks like. There we go. So this is what we're going to want. It starts with the smallest, and it gets larger as we go from left to right, going on to the next line, getting larger and larger as we go, from right to left. Right to left, it gets bigger. But we haven't actually assigned this to anything, so it's just showing us what would happen if we did apply this to the first 40 rows. So let's go ahead and do that. Let's see. So I'm going to say zmat at the first 40 rows is equal to the transposition of this apply function, blah, blah, blah. And I think that will do what we want, but maybe not. Let's find out. Okay, it looks like the smallest value is 0.00003. That's correct. And then they get larger as we go to the left. We have 10 columns. What happens here, once we hit the 50th percentile, they flip and they start getting larger as we go from left to right. So we've done it. We're very close to having our Z table. This is basically what we want. But now we need to format it just a little bit. So I'm actually going to turn this into a data frame. Maybe I should do it as a tibble, but tibbles don't really have row names. And I really shouldn't use row names. You're not supposed to, but I'm going to because I want to for this particular application. So I'm going to make this into a data frame. To turn ZMAT into a data frame, I'll say it is equal to itself as a data frame. So it's ZMAT is equal to itself as a data frame. All right, so that happened. Now it is a data frame. If I ask what is the class of ZMAT, why, it's a data frame, it says, because you just told me it was. Okay, cool. That sounds good. So now this allows me to add row names and column names, and that's what I'm going to do. All right. The column names are the call name. So you can use this function call names to name your columns. It's a combination of things, and I'm just going to list these things out. 0.00, and where I'm getting this from is right here. 0.00, 0.01, 0.02, 0.03, etc., up to 0.09. And now almost all of this code is redundant, so I'm just going to speed this along. I can hardly see my screen. 0.02, whoops, 0.02, 0.03, 0.04, 0.05. There we go. I'm just copy pasting the redundant part. All right, the sun is starting to block my view. I'm going to have to turn this. I'm going to have to do something. Wow, that was bright. There we go. Kind of. All right, so those are our new column names. Let's see what it looks like when we assign those. Okay, you can see the column names have changed. Now we've got 0.00, 0.01, 0.02, etc., all the way up to 0.09. That's what we want. Let's do the same for the row names. So this will be slightly more of a pain, I think. Yeah, because I need to add a -0, and that's going to be a bit of a pain. So let's see. I'm going to say Z row, not the numeral 0, but Z, the rows of Z rows. This is going to be a sequence from -3.9 to +3.9, because remember, in this column, we just have Z-scores to the 10th place. Okay, and we're going to go by 0.1. Let's see what we get. That is not what I wanted. This is very close, but I have like 3.8999, and I wanted it to start with 3.9. Now I could sit here and try to figure out why is R doing this to me. Maybe R is just doing this, but it feels like it's doing this to me. But I'm not going to, because they're all within rounding error of what I want. So I'm just going to say, who cares? Let's just fix this by rounding to 1 decimal place. Done. There we go. Now it's fixed. Okay, now I'm going to insert another 0. In fact, I'm going to insert a -0. Let's see. So to do that, first I'm going to find the position of that 0. It's at the 40th position. So now I'm going to say 0 is equal to a combination of things. It's itself for the first 39 scores. Then it's a -0.0. And I have to do it like that because I don't think R is going to recognize -0. I don't think that really means anything. Then after that, proceed again with the remainder of positions 40 through, what is the length, 79? Let me see how many there are. Yeah, there are 79. So 40 through 79. Okay, let's see what this looks like. All right, you can see the values have all gone into, let me move this up. You can see the values have gone into quotation marks. They're all characters now. I've just coerced them all into characters because I did it to one of them, and that's fine. I don't need to do any math with them, so it's not a problem. Let's just make sure we're still good. Okay, but I see something I don't like. I see -3, and -1 and 0. So anytime there's an integer, it's not giving it to me to the 10th place. So I'm just going to replace those values real quick. Maybe there's a faster way. I don't know. This is how I'm going to do it. So first, let's see. Where is that -3? Whoops. I used a 1 equal sign and I needed to use 2. Here's a quick sidebar. Equal sign versus 2 equal sign. In fact, to avoid this confusion, some people will use this symbol, an arrow, but I don't do that because that's 3 keystrokes on my keyboard, whereas equal sign is 1, and that's just, I'm not going to hit 3 keys when I can hit 1. Sorry, there's a plane passing overhead. Don't know if you can hear it. So when you have a single equal sign, think of this as like a command. You're assigning something. It can actually do a few other things as well, but think of it as like you're telling it. So like if you said x is equal to the values 1 through 3, R would be like, okay. If you say give me x, it'll be like, it's 1, 2, 3. Like you said it was, so it is. An equal sign is more like a question. So if I was like, x is equal to 1 through 3, it would be like true, 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 true. Because it's based on the information it has. It's like, yes, it is. So that's how I distinguish it. I'm either I'm saying something is equal, or I'm sort of asking if something is equal. Okay, so I'm asking which position is equal to -3 in that vector, and it's 10. I have a suspicion this will be 20. Yep. Then 1 will be 30. What is 0? 30, 40, 41? Yeah, 41. Okay. 51. Okay. So I'm going to replace those values. I'm going to say 0 at several things, so combination of things. At 10, position 20, 30, 41, 51, 61, and 71, because those are all the integers that are showing up in a way I don't want them to. I'm going to reassign them. These are now a new combination of things. Those things, the things at those positions are now, what? Negative 3.0, negative 2.0, negative 1.0, 0.0, 1.0, 2.0, 3.0. And then I'm also going to tell it to show us the result after it's done. Yeah, that looks good. That's what we want. Now we have negative 3.0, so everything's to the 10th place. It didn't have to be that way, but I'm weird. I like things to be consistent, so I did it. Negative 1.0, negative 0.0, positive 0.0. And listen, I promise, once we get to the other tables, they're going to be so fast. We'll do them in like 2 minutes. So much faster than this one. But we're basically here. So let's say our row names for our Z matrix, they are now equal to this Z row vector that we created. Okay, this is looking good. Actually, I'll do the view function. Yep, so the column off to the left looks like I want it to. All the correct proportions are listed. We have the z-scores to the 100th place up top, and we have all 80 rows listed. So let's go ahead and turn this into a more viewable table or export it. I'm going to use a library called h²-table. You don't have to do this. There are other packages you could use, but I like this one. Sorry. I'm near an airport. There's another plane. Okay, so yeah, let's make a flex table. I'll say table 1 is equal to a flex table, and then I'm just going to throw the Z matrix in there. So the flex table for the Z matrix. Let's see if that works. This is good. This is very close to what I want. The only thing is, I'm not getting those row names. The row names aren't showing up. So I'm going to have to do something to force them to show up. I'm going to make it, let's go from row names. I'm going to make it turn its row names into a column called Z. Did it work? There we go. Okay, so now we have everything we want. We have a column called Z, which has those row names I created. I probably could have avoided this by just making it like a tibble and then just adding this as another column, but whatever, this worked. We even have our duplicate values of 50th percentile for 0 and -0. So yeah, this is basically there, and it's ready to export. You can export a flex table like this. You can say print print this thing I called table 1, which is just a flex table of the matrix. And I'm going to say preview equals docx for this is to print to a Word document. I could do it to a PDF, but earlier when I tried it, I got some kind of error. I need to update something, and I'm too lazy to do that right now. Okay, here we go. And this is looking pretty close to what we want. Like, you could do some formatting. You could be like, this is a Z table. Add instructions for how to use it if you want. But this is pretty much there. This is, this is very similar to the example. All right, so there you go. There's how you create a Z table. More of a pain than the others, I'll say that. So the next task, this will be so much faster by comparison. We're going to create a table of critical values for T statistics. Now, there's a different distribution, a different T distribution for each degrees of freedom. So the fewer degrees of freedom, the more spread out the distribution is. And then as your degrees of freedom get larger and larger toward infinity, it becomes more and more like a normal curve. But that means there are an infinite number of tables for the T statistic, and that's a problem. So what we do here is we pivot and we just start giving critical values in the table. Instead of all the proportions, we just give the critical values. And so we say things like, for example, if you're doing a two-tailed test and you want to use an alpha of 0.05, well, the critical value, if you have 7 degrees of freedom, is 2.365. So these are sort of like shortcut versions of all those different tables, where you just say, I'm looking for that 0.05 proportion, well, here's what it would be if it was this table or that table or this one, et cetera, et cetera. And we commonly just do it for some of these alpha levels like 0.1, 0.05, 0.01. Now, a t-test it can be a two-tailed test. So if the reason I chose these values is because they lend themselves well to alphas like 0.05, 0.01, and so on. If you're doing a two-tailed test with an alpha of 0.05, that's right here. But if you wanted to do a one-tailed test with a 0.05 alpha, just go over here to this column, slice your alpha in half, and that will give you the critical value for a one-tailed test with an alpha of 0.1. Similarly, if you wanted an alpha of 0.01 with a two-tailed test, that's this column. But if you're doing it with a one-tailed test, that's this column, because it's a 0.02 cut in half. So I've only shown the results for two-tailed tests here, but there are different ways you could explain it. I also did a 0.001 in case you're like really stringent with your hypothesis testing. And I'm going to show this going from 1 degree of freedom all the way to 100, and then I'm going to jump a little bit up to infinity. And we'll see some of these characteristic values like 1.645, 1.96. Those are critical values you will see again in your life, probably. If you're watching this video, you're going to see them again. Okay, so let's do it. This will be much easier. Let's get back into R. Now we are, what is going on? Sorry, can't see what I'm doing. We're going to create a T table. I don't know, is that what it's called? T distribution table? Something like that, table of critical values. Okay, the code that we're going to use is Qt. This finds the critical value for a T distribution where you're looking at a certain proportion and with a certain number of degrees of freedom. Okay, so for example, if we wanted to know which T statistic is at the 5th percentile. If we had 10 degrees of freedom, well, it's negative 1.81. Okay, so we're going to use that sort of approach to build a table. And it's going to be way more streamlined than what we did before. So let's say t-dist, that's our t-distribution. I'm going to make a tibble because it's very convenient for what I'm about to do. And let's see, so I'm going to say, let's just look at our example. So our first column is going to be called df for degrees of freedom, and it's going to range from 1 to 100, and then we're going to add infinity at the end. So this first column is called df, and it is a combination of things. It's 1 through 100, and then I'm going to put the infinity symbol. You can represent infinity with capital I and F in R, but I don't literally. These are just names. These are just things I want to show up on the left-hand side, not actual numbers I need to use for calculations. So that's my first column. The second column is going to be called alpha equals 0.1, and that is going to be equal to, we'll use this QT function, and let's see, we would use 0.95. 0.95 with, well, we'll come back. I'll put this as a placeholder. We'll need to know the degrees of freedom before we move on. But why did I choose 0.95? Because the t-distribution is symmetrical. So if my alpha is 0.1, that means I want the value that plus or minus whatever value that cuts off the lower 5% and the upper 5%. So whatever t statistic is at the 95th percentile, that is the value that does it. So for example, let's just check real quick. If it was the 95th percentile with 10 degrees of freedom, it's 1.81. So correspondingly, if I could go check, I could be like, well, what's at the 5th percentile with 10 degrees of freedom? It's the negative version of the same thing, because the one cuts off the top 5% from the rest of the distribution, the other cuts off the bottom 5%. So this is going to give us what we want. It'll give us the alpha level. If we're using a 0.1 alpha level, it's going to give us the critical values. Now for the degrees of freedom, I'm just going to say, well, I would like you to do this several times over, iterate through the values 1 through 100, and also do it for an infinite number of degrees of freedom. Let's just go ahead and see what we get when we do this. I have screwed something up. I'm missing a closing parentheses. There we go. Did it work? Let's say view our t-distribution. There we go. Yep. So we've got degrees of freedom in the left-hand column ranging from 1 to 100, then infinity. And we have the critical values if alpha is 0.1. And the bottom one should be 1.645, and it is, because that's what it is when you have an infinite number of degrees of freedom. So this is showing up the way that we want it to. It's iterating through all these degrees of freedom. Okay. Although I kind of don't like how many significant digits we've got. I'm going to round that off to 3. So I'm going to round whatever the result of this, I'm going to round it to 3. Okay. So we should be in good shape now. So I'm gonna need that for 0.05, 0.02, and 0.01 and 0.001. And always copy when you can. So this one will be 0.05, this one will be 0.02, this one will be 0.01, and this one's 0.001. We need to update these proportions. We're now looking at the 97.5th percentile, because there's only 2.5% of scores that are more extreme above. So if we're thinking about the negative version of that, there's only going to be 2.5% below. 2.5 plus 2.5 is 0.05. And this is a 2-tilt test. If you want to check my math, we could use this formula. You could say 2 times, open parentheses, 1 minus 0.975, and you're going to get 0.05. So that is going to give us what we want. For the 0.02, we need to go to 0.99. We can, maybe you can see why that's the case. Only 1% above. It also is the same as whatever. So whatever t statistic is at the 99th percentile, the negative version of that is at the first percentile. Add them together and you get 0.02. So that's going to do what we want, but you can double check it like this. Those add up to 0.02. Here we'll use 0.995, and here we'll use 0.9995. And you can check my math if you want. That will give us a 0.001 alpha. But anyway, that's how we're getting these, because these are two-tailed tests. So let's see. This should work. Let's run it and find out. There we go. All right. So the critical values are larger when we have fewer degrees of freedom, and then they're dropping off. We should have a 1.96 at the bottom for 0.05, which we do. Yep, these all look correct. So there we go. There's our t table. I think that's basically how I want it to look. And the way I named the columns was whenever I assigned them. That's how you can create a table. You can name the column and then say what it's equal to. That's why that worked like that. Okay, let's make it a flex table. Table 2 is a flex table of this t-dist thing. Do that and show us what it is. That already looks good. I like it. Let's export. So we'll print table 2, preview equals docx. Okie doke. Here we go. Now you could beautify this a bit, but it's pretty much ready to go. There's your t distribution, or your table of critical values for t. So that one was a lot faster. Let's take a look at an F table. How do we create one of these? Now, these are the same sort of thing. It's a bunch of critical values, but along the left-hand side, we have degrees of freedom in the denominator of the way the F statistic is calculated. It's a ratio, so degrees of freedom in the denominator, and then each column represents a different number of degrees of freedom in the numerator. Here, I've got us going from 1 to 10, then jumped up to infinity for the numerator, and I've got 1 through 100 for the denominator, and then jumped up to infinity, just because it's kind of fun to see that when you have infinite degrees of freedom on top and bottom, an F statistic 1 would be the critical value. So literally any amount of evidence or any amount of variance more than chance would be statistically significant if we had an infinite number of degrees of freedom. That's kind of off on another topic though. So let's create this distribution. Well, let's create this table. Where's R? Here is R. Let's get rid of this. Creating an F table. Okay, so for this one, I am going to create a vector called DFD, degrees of freedom in the denominator. These go from 1 to 100. It also includes infinity. Let's see what that looks like. There we go. We're gonna need those here in a minute. Now I'm gonna create something called the F dist, kind of like our t dist before. We're just gonna make a tibble. All right, this first one, what do I call it? I called the first column df denominator. So that's what I'm gonna say. That is equal to, well, a combination of things, 1 through 100, and then also the infinity symbol. Oops, that's the A symbol. Oh God, still the A symbol. There we go. There's the infinity symbol. Then what do I call these? So I'm going to need to do something fancy here. I'm actually going to need to download another package. I could probably do this using FlexTable, but I don't know how. So I'm going to load something called RimPsych, which has some nice tabling abilities. It uses FlexTable. But anyway, I'll show you what it can do here in a minute. So to make this work, I want to make this line appear up top above these. So I'm going to name them something different. I'm actually going to use this kind of name. I'm going to say, this is going to be numerator dot 1. And what that means is things that land under, whoops, I'm going to call it DF, degrees of freedom in the numerator dot 1. That's going to be this first column, which is just a 1, and it's nested within this DF numerator label. Okay, then I'm actually going to do that for all of them. I'll just do that real quick. The things I do to save time often end up taking more time. How many did I go to? I went to 10. Then I went to infinity. Right? Didn't I? I did. There we go. Okay, cool. So you'll see how that works in a minute. But anyway, this is going to be, let's see. I'll round. How did I round these? I rounded these to the hundredths place. So I'm going to say round something to the hundredths place. And what am I going to round? Oh, yeah. So before we were using QT to find critical values in a T distribution. Well, now we're looking in an F distribution. So we're going to use QF, I think. Yep, there we go. And you can see, well, I don't know if this is showing up, but it's asking for these things. It wants to know the proportion we're looking for. It wants to know the degrees of freedom in the numerator and the degrees of freedom in the denominator. There might be a way to do this by looping, but I don't know what it is. So I'm just going to do it in a series of commands. So we're going to say QF, open parentheses. What am I doing? Okay, so for these are all going to be using an alpha of 0.05. So this entire table is for 0.05. Hold on, car passing. Sorry. So this table, just every single one of these critical values is for an alpha of 0.05. We need a different table if we're going to use an alpha of 0.01, for example. So I'm just going to use 0.05, which means I need to use the proportion will be 0.05, or I could use 0.95 actually, because we really care about the upper proportion. All F tests are one-tailed tests. We only care about the right side of the tail. So, I mean, that's not all we care about. That's where our critical region is. So I think I can just use 0.95. So we're going to have 1 degree of freedom in the numerator, and then I want it to cycle through these options for the denominator. I want it to do all of 1 through 100 and also infinity. So I'm going to say, sorry if this is hard to read. So the proportion, whatever's at the 95th percentile, 1 degree of freedom in the numerator, and then DFD in the denominator. So iterate through all of 1 through 100 and infinity. Yeah, will that work? I think this will work. So I need to replicate this for all of these, but I need to change the degrees of freedom in the numerator. So that becomes 2, 3, 4, 5, 6, 7, 8, 9, 10. And then here, I also need to do it for infinite degrees of freedom in the numerator. So I'll say INF for infinity. Now, I may have done this wrong. This is the first time I've ever written the code like this, so I might have screwed it up. Let's find out. Let's see if this works. What happens whenever I say run that and then show it to us? That looks correct. Yeah, I think so. 161.45, then 199.5. Over on the right, it should be 254.31, and it is. 241. Okay, yeah, I think it worked. Let's scroll down to the bottom. We've got a 1 at the bottom right corner, which is what we hoped for. We've got a 3 for an infinite degrees of freedom in the denominator and 2 in the numerator, which is what we had before. Okay, yeah, so I think this worked. Now comes the fancy part where we make it look nice. Let's turn this into a flex table. How many have I made? I think this is the third one. So flex table of, actually, I'm going to pivot. Now I'm going to go to nice table. This comes from RimPsych, that RimPsych package that I was using. I think I loaded it already. Yeah. So I'm going to create a nice table. Which he basically has worked with Flex Table and like set a bunch of options so that they'll show up in APA style, which I really like. So I use a variation of this whenever I'm publishing. So a nice table of the S distribution, and I'm going to say separate dot header is true. And what that's going to do is, if I do it correctly, what that's going to do is, yeah. So it has split it up. It's displaying everything like we wanted, but then at the top, it nested each of these numerator degrees of freedom within this heading of DF numerator. I don't exactly like how this looks, and I could change it, but I'm probably just going to change it once I export to Word. So let's do it. So the way that worked was because I used this format where I said DF numerator dot infinity or whatever, and then whenever I say separate the header, make that true, it slices it up so that infinity is nested under DF numerator. So hopefully that makes sense. I'm sure there's a way to do it in Flex Table, but I don't happen to know how, and I do happen to know how to do it with RimPsych, so I just ran with that. Let's export print table 3 preview equals docx. What do we get? We've got some spillover. I'm going to pivot to landscape view. There we go. That looks better. I'm going to drag this away a little bit. All these settings could be changed in R, but I'm not going to because this is also pretty easy. Okay, that looks not bad for a table of critical values for the F statistic, which, when have you ever heard of a table of critical values for the F statistic looking good? So there we go. Okay, what's left? The last thing, and you can see I made it slightly prettier for the version that I'm sharing with other people, but you could do that. Okay, what's left is the chi-square distribution. This will be extremely similar to what we did with the t distribution. You can see the format is even the same. It's always a one-tailed test. I've just got degrees of freedom 1 through 100, and then the same alpha levels as we did with the t table. It should look extremely similar. All right, so because of the similarity, I am going to copy my past work so I don't have to do it all again. All right, new section. Creating a chi-square table. Okay, now I need to update all of this stuff. So this is a chi-square distribution. That's what I'm going to call it. I'm not going to go to infinity this time. I'm just going to go from 1 to 100 for the degrees of freedom. All of these column titles are correct. We want 0.1, 0.05, 0.02, 0.01, 0.001. So those titles are already correct. We're no longer going to use QT. Now we're going to use something called Q chi SQ for chi-square, but it works the same way. Put in the proportion and the degrees of freedom. So Q chi-square. I'll just replace all these real quick. Okay, now I need to change the proportions. This is a one-tailed test, so I'm looking, if I want to slice off the lower 90% from the upper 90%, I need the 90th percentile. If I want to slice off the lower 95th percent from the upper 5%, I need the 95th percentile. Similarly, the 98th percentile to get the 2% above, 99th for only 1% above, and 99.9th for only 0.1% above. And I think it's already ready. I'm going to call it chi-square test. Let's see if this works. I did something wrong. Oh, when I was doing the t-test, I was asking it to also go to infinity, but in our example, we're only going up to 100. Let's try it again. Did it work? That is, excuse me, that is not what I wanted exactly. Oh, there we go. Typo. Okay, that looks good. I haven't memorized these values, so I don't know if that's right or wrong. Let's do some spot checking. We should have 2.706, 3.841, 10.828. Then down, let's go down to the bottom. We should always double check your work to make sure it comes out correctly. This stuff can get to going, as you can see, it starts getting really fast once you've already written the script, and you want to be careful that you don't fly so fast that you make mistakes and never even notice. So double check everything. But all of this looks right. Okay, this will be table 4. It will be a flex table of this chi-square distribution. Do that and show it to us. Beautiful, beautiful. Love it. Okay, sounds good. Let's print it. See what it looks like. This is the beauty of R. So these things are a pain to do the first time, but you may have noticed it just got faster and faster the longer we were going because we start being able to copy our previous work. And that's what's nice about R. Once you've solved a problem, you've essentially solved it forever, and you can always refer back to that code in the future. That's what I love about it. One of many things I love about it. Okay, here we go. Here's our chi-square table. It's a thing of beauty. There we go. And like I said, if you don't like these numbers, if you're like, I want to know what it would be if I had 127 degrees of freedom, just go to 127 instead of 100. So yeah, that's it. That's how you do it. Hope you had fun. I can't imagine very many people would actually sit through something like this. Probably just stats nerds and people who are trying to learn more about R. But I enjoyed doing it. It was kind of fun to do one where I either can't make mistakes, or if I make mistakes, they just get left in. That was kind of fun. It also means I won't have to spend very long editing it. So anyway, there you go. We've created our own Z table, aka unit normal table, our own T table, F table, and chi-square table. And you could do this for anything. If you wanted to get a table of the significant or the critical values for correlations of particular sample sizes, degrees of freedom, you could do it using the same kind of procedure. You just need to work out what code will give me the proportions I need, and then just follow this sort of process. Okay, so that's it. And I probably need to stop talking because I think I can just sit here and just keep making up things to say forever. So I'm going to stop now. Okay, have fun. Bye.